Greetings, ladies and gentlemen. My name is Abdul Moin. I am Field Application Consultant for Static Verification, CDC, RDC, and related products for Meta Graphics, which is a Siemens business, which now is called Siemens EDA. This paper, titled Bringing Reset Domains and Power Domains Together, Confronting Issues Due to UPF Instrumentation, is an outcome of our efforts in cleaning power-aware RDC for NXP SoC designs. We worked with a very knowledgeable engineer Inayat Ali from NXP Semiconductors and tried solving problems we faced in the process. Along with us, our colleagues in the Mentor Graphics, Manish Bhati and Manjunath, worked with us in solving these problems, creating various scenarios, and coming up with the methodology for the task. We would like to share our learnings and experiences through this paper. I will now request my friend Manjunath to take us into the details of our discussion. Over to you, Manjunath. Thank you.
Let us understand first how metastability issues is caused by reset domain crossing paths, which is also called as RDC paths in short. RDC paths are formed when data is crossing from one asynchronous reset domain to another asynchronous reset domain. So when I'm referring to issues caused by RDC paths, I am primarily considering reset assertion problems and not the deassertion issues. So here we have R1 as the TX flop, which has a TX reset RST2, and R2 is my RX flop, which has the RX reset as RST2, and CLK is my common clock for both the flops. Say suppose RST1 is asserted very close to the passage of the clock. This will cause the Q1 to immediately go low within the setup and hold window of the clock edge. And now if RST2 is deasserted during this cycle, the Q2 flop will sample this transitioning value from the Q1 and R2 flop will suffer metastability event. So this is how reset domain crossing paths can cause metastability. Problems faced during low power aware RDC verification. Let me take some time to go through each of the problems in brief, and we have tried to explain in detail each of these problems in the upcoming slides with the help of the scenarios. Today's complex SoC design introduces many challenges. Complex SoCs have many independent functional blocks. The blocks may be having different booting and clocking protocols, leading to introduction of reset domains. Interaction between the reset domains lead to various RDC problems the designers ought to verify. Also, there can be multiple power domains that may further lead to an increase in verification complexity. Along with low power verification for functional correctness, designers also need to validate that the power control logic does not introduce new multi-clock and multi-reset issues into the design. UPF instrumentation may lead to higher number of new resets that are not part of the design specification. Resets that are not part of design specification may lead to increasingly complex RDC results, which in turn may increase the verification effort because of higher number of violations encountered in a static verification tool. Let us now understand how metastability issues are caused due to data interaction between different reset and power domains. For example, consider there is a data transfer from an source reset domain to a destination reset domain. If source reset asserts asynchronously very close to the active edge of the destination clock, that is, within the setup and hold window, destination domain samples the output transitioning value and suffers meta event. This scenario becomes even more critical when power control elements are introduced in the design. Ignoring such cases will have a huge impact during the reinitialization of registers, preventing the designs to reset to a known good state and sampling the retained values when the devices power up. The power control logic can add or break the RDC paths. To explain this, let us consider the scenario where isolation cell is placed in the design. There are high chances that combinational logic may get introduced between synchronized path breaking the synchronization logic or causing potential glitch issues. Also, the insertion of power elements may introduce new reset domain crossing paths if the control logic to power element is driven by a different reset domain, unlike the source and destination reset domain. Such scenarios can also be evident in disrupting the safe RDC paths, making them unsafe crossings. Challenges faced during the application of active power management techniques. As we all know that active power management involves the application and control of power reduction techniques like clock gating, power gating, dynamic voltage frequency scaling to minimize the power consumption. Let us now consider one example for dynamic voltage frequency scaling technique which has a downside to it. Studies have shown that synchronous clocks on voltage domain using dynamic voltage scaling technique will behave asynchronously relative to the all other clocks in other voltage domain. This means any synchronous crossing to or from voltage domains will cause metastability. These voltage domain crossing paths must be treated in the same way as clock domain crossing paths and must be synchronized in the receiving voltage domain. Similarly, all the synchronized reset domain crossings will become unsafe crossings if there is a data interaction happening between different voltage crossing domains. Different kinds of RDC paths in UPF instrumented design. Now that we have understood what is RDC crossing and how it causes metastability issues when different reset domains interact, let us now see some examples of different kinds of RDC paths when UPF power specification is added to the HDL design logic. Insertion of isolation mux select whose enable signal comes unsynchronized from a different reset domain TXRST creates a new RDC path. Without the power aware logic, no crossing exists in the design. Second example here describes how UPF adds combinational logic to a safe RDC crossing. This can lead to potential glitch issues, creating unwanted transitions to be sampled in the downstream logic. Similarly, we have other scenarios like when UPF adds retention registers in the design, whose restore and save ports are driven by a different reset domain. It is very important for a designer to verify such cases of RDC paths or reset domain crossings when power elements are placed along the reset path, clock, and data control paths in the design. Analysis and results. Consider the following table which depicts a real design scenario where UPF instrumentation led to an increased number of inferred clocks and resets, where we saw a +7 increase in the clocks and +20% increase in the resets after the UPF instrumentation to the design. We found out that the rise in inferred clocks and resets was mainly due to addition of extra combinational circuitry in the reset and clock paths. These clocks, these extra clocks and resets are due to gated mux and gated combo logic due to UPF instrumentation of power control logic. Because of the change in number of clocks and resets, many crossings were marked unsafe. For example, safe crossings that were marked ordered reset crossings got changed to unsafe asynchronous reset to asynchronous reset crossings in the design, disrupting the reset ordering sequence. Additionally, combinational logic before synchronizer crossings were also reported in the UPF instrumented design. Overall, we saw a +23.6% rise in the total number of violation count compared to the non-UPF design run. Most of the extra violations were the result of instrumentation of isolation logic cell whose select was driven from a different clock or reset domain. We have investigated some scenarios which need designer and verification engineers' attention and must be resolved for a healthy design. The next slides discuss some of the common scenarios which we have encountered during UPF instrumentation. Let us now discuss some of the real-world problematic scenarios leading to RDC issues due to insertion of low-power elements such as isolation cell retention logic level shifters. We will discuss each of these scenarios in our upcoming slides. Please note the different color coding in the schematics indicates the specification of different power domains used in the design. Scenario 1, isolation enable in different reset domain. Without UPF instrumentation, there was no RDC crossing between the UF4 and UF2 registers, as resets for both the registers were the same, which is RST1. But with the insertion of isolation cell whose enable is driven from a different reset domain, RST3, we have a new RDC crossing between UF4 and UF2 registers because the UF2 register is now actually controlled by two different set of resets, RST1 and RST3. So with this example, we have understood that with the insertion of power elements, new RDC paths arises in the design. Scenario 2, isolation cell disrupts reset ordering sequence. Before UPF instrumentation, the flops UF1 and UF2 are in different reset domain, RST1 and RST2. But the crossing is safe if a reset ordering sequence is provided between RST1 and RST2 in the design, where design specification says RST2, the RX reset, is guaranteed to occur before the TX reset, which is RST1. The problem arises once when the UPF is instrumented in your design. So in this case, once the UPF, the power isolation cell is inserted in your design, whose enable is driven by a different reset domain, RST3. This disrupts the reset ordering sequence between the RST1 and RST2, and thus there is a new RDC crossing formed between the RST3 and RST2. Scenario 3, isolation cell placed in control path of reset. In this scenario, reset of flop UF3 is controlled by an AND gate. The control signal at the input of AND gate is driven by a latch, and UF3 flop is in reset 1 domain. After UPF instrumentation, isolation cell is placed in the reset control signal path. Now isolation cell enable signal is in RST2 domain. This leads to an additional inferred reset at the output of AND gate, as both the inputs are now driven by a different reset domains. This adds an additional RDC path in the design, forming a crossing between UF4 and UF3 in the design. Scenario 4, isolation cell placed in reset path passing wrong clamp value. This scenario is very much similar to scenario 2, which we discussed in the previous slides, where insertion of isolation cell disrupts reset ordering between RST1 and RST2 resets and creates a new RDC path between UF1 register and UF2 register. There is also an additional problem here, that is, since isolation enable is driven by a different reset domain RST3, isolation cell can pass the wrong clamp value when the source power domain is off, such that it makes the UF2 flop deasserted, putting the UF2 register in a non-reset state, causing metastability at the RX flop UF2 when the source reset RST1 is asserted asynchronously. With UPF instrumentation, safe reset ordered crossing changed to unsafe reset crossing. In this scenario, asynchronous reset RST1 is driving data path which can cause metastability in the UF2 flop. In non-UPF design, UF2 is reset with RST2, and let us assume there is a reset ordering sequence specified between RST1 and RST2. So this can be considered a safe crossing in the non-UPF run. With UPF instrumentation, isolation enable is in different reset domain RST3. This disrupts the actual ordering between the resets RST1 and RST2 and hence makes the crossing unsafe. Also to note, isolation cell being a combination logic will bring in the potential glitch issue in the reset path. Scenario 6, isolation cell instrumented in clock gating isolation signal. Clock gating isolation RDC paths which are safe in RTL are no longer safe with UPF instrumented RTL. Clock gating isolation is a special technique to stop the metastability issues from occurring. This technique anticipates the RST1 asynchronous reset activation at UF1 flop and preemptively isolates the UF2 domain logic by deactivating the receiver logic clock of UF2, thereby avoiding metastability propagation to UF2 logic. With UPF instrumentation, the isolation cell is inserted in the clock gating enable path. If U underscore lat powers down, and since the clamp value is 1 bit 1, U underscore lat will no longer be able to deactivate the RX register clock of UF2 flop, and this will lead to unsafe crossing between UF1 logic and UF2 flop, as both are in different reset domains RST1 and RST2 respectively. Scenario 7, DVFS technique, also called as dynamic voltage frequency scaling technique, makes the synchronous paths to an asynchronous path. In this scenario, UF2 underscore sync and UF2 flops are in different voltage domains. This scenario depicts the issues in the design that implement DVFS techniques. Here, path between the UF2 sync and UF2 behave asynchronously, as now the common clock CLK1 will lose its phase relationship to its attenuated or amplified version of UF2 clock. In other words, the clock CLK1 reaching the UF2 flop is level shifted. Hence, reset RST1 deassertion will no longer be in sync with UF2 clock, which causes reset deassertion issues in the design. Scenario 8, source to TX driven by different clock leading to metastability issues in the retention logic. In the schematic, it seems that both the TX UF2 and RX UF3 registers are driven by reset RST1, but TX is actually driven by a source register UF1, which is in a different clock domain CLK2. This leads to metastability issue as the change at the input of source register to TX, that is UF1, can cause an asynchronous assertion of TX flop UF2. Thus, new RDC crossing is formed between the UF2 register and retention logic UF3. Proposed new rule check sets. From our experiments, we have observed that when low power elements are used in the design, there is a strong need to define some of the new rule sets for reset verification to ensure the correct propagation of resets and reset connectivity to the blocks which are in on and off power states. Let us discuss each of these check sets in detail in our next slides. Check 1. Asynchronous reset signal is driven by isolation logic is always active due to clamp value. In this scenario, when the source power domain is off, the isolation cell driving the clamp value 0 makes the register UF1 to remain in reset state always. The resolution here is to ensure that the correct clamp value is used. Check 2. Isolation enable is driven by different reset group. Isolation enable is driven by different reset group, RST3, and this may lead to new RDC path in the design. The resolution here is to specify the correct reset groups with respect to TX and RX domains for the isolation signal, or to specify the correct reset ordering sequence. This check ensures to resolve the new inferred resets due to the isolation sets. Check 3. Reset is driven by power off domain. In this scenario, the resets driving UF1 flop and UF2 flop are always driven by power off domain. So we need to ensure the correct power states are defined for such reset generator logics in the design. From observations, we have noticed that there is a need to define the methodology to incorporate certain issues which may creep in due to power instrumentation. An efficient methodology can help the design and verification engineers upfront to verify the RDC paths for the power-aware designs. Adding power control logic may lead to higher number of resets in your design. All the new resets must be resolved before doing RDC analysis. Also, adding power control logic may lead to higher number of clocks, leading to higher reset domain crossings, spanning different clock domains, as well as reset deassertion issues. All the new such clocks must be resolved before doing RDC analysis. Insertion of power control logic may disrupt existing reset ordering sequence specified in the design. Review the newly created resets by examining the reset tree report and check if the newly created resets has in its fan-in a reset which is part of an existing reset order. If possible, ensure that the control signals of the power control logic are from the RX reset power domain. Incorrect clamp values of power control strategies can reset the fan-in logic incorrectly. Ensure that the correct clamp values are defined, and also the design characteristics as well as the power control strategies such as isolation cell, retention logic, level shifters on the reset and data path are correctly defined. This methodology successfully helps us to sign off the RDC results by exhaustively verifying for the structural and functional reset domain crossing issues in the UPF instrumented design. So to conclude in this paper, we have shown how metastability issues can be introduced by UPF instrumentation in reset domain crossing space. Insertion of low power elements increases dramatically new resets, which in turn will have a huge impact on RDC paths crossing various power domains. We have also suggested few RDC rule check sets for correct reset propagation and reset connectivity to on and off power states. We have also explored an efficient methodology to deal with the low power RDC issues, which otherwise results in a higher verification turnaround time and unnecessary ECOs and costly respins if it is undetected.